One of the important topics that we need to cover in organic chemistry is the idea of acids and bases, and in this case we're going to talk about what is called acid-base equilibrium, or acid dissociation constants. And I want to show you the basic idea, or the simple idea of an acid. Now, if this is a strong acid, and most of you have done this before, but if we have a strong acid and it dissociates 100%, then that's considered to be a strong acid. In other words, when it dissociates completely, and so we have hydrogen and the conjugate base here. Let's make sure now we can call that a proton, right? And then this is what is called the conjugate base. It was an acid, but once it lost its hydrogen, it now has basic properties because there is an attraction of this A- or anion for the H+. But that's not true with a strong acid, so we have to explore this a bit more, that conjugate base concept. Okay, but the general idea is that if it breaks apart 100%, then we call that a strong acid. Now we can also use the representation HA for a weak acid. And generally weak acids, they set up what's called an equilibrium. And so now this back and forth motion, this reversible arrow, or this double arrow here, that stands for equilibrium. We still have the proton, we still have the conjugate base, but the dissociation is more like 10% and probably 1% or so. And that tells us something about the conjugate base here. This time the conjugate base, and we'll just call that CB, that conjugate base now does have attraction properties towards H+. So what's the difference? Well, we've spoken about this before. In this situation above, with the strong acid, we have the water molecules HOH. And so you have the partial positive, and then you have the partial negative, a double partial negative, if you will. But let's just call this the water boomerang, for example. We can surround this with the positive sides of the water, and so there's such a strong attraction of water for this that conjugate base cannot come and reach with the H+, so there's no attraction there. So they don't come back together, but that's not true here with the H+ and the A-, plus the attraction of this A- with a weak acid situation is that's a very strong attraction, because this only happens with a value of about 10%. I want to show you something called a Ka expression. Not all of you have seen this. You have if you are from AP Chem. There's a Ka expression. And here's what happens is you take the product H+ and A- and you divide by the original concentration. So remember that this is molarity. Drew that a little bit off, but you get the idea that that's molarity, and it stands for moles per liter, so that's a kind of an international thing. And so we can now measure these acids by this value that comes out here. And I want to give you an example for our first one is acetic acid, HC2H3O2, and it forms an equilibrium. And this is going to be important for organic chemistry purposes. So what do we have? Let's make sure we understand that this equilibrium arrow, or the double arrow, means that the forward and the backward reactions are going at the same rate. In other words, the forward goes at so many miles per hour and the reverse goes at the same speed. Now it's moles moles per liter per second, but hey, miles per hour works pretty well for us. So it's going 20 miles an hour this way and 20 miles an hour that way. But you could have a situation where you have something like this, and then you have a lot of this here, and then maybe on the other side you have very little of whatever's on this side, okay? But the rate going back and forth, right? The rate going back and forth is the same. The Ka value that we have for acetic acid is 1.8 times 10 to the negative 5. And what that means is the ratio of H plus and that product there over HA is actually equal to 0.000018. That should tell you a couple things, but first of all, it tells you that there's very little H plus, little A minus. There can't be a lot if that's the ratio. In other words, if you have acetic acid in water and it dissociates, it only produces a very small number compared to its original concentration. Okay? So that's what this number tells us, is that if you have a really small number, then this A minus does not like to be alone. A minus is not stable. Okay? It's not stable. If it was, for example, then it would be okay on its own, but it doesn't happen that way. So we need to remember this. A minus is not stable when the Ka is something like 10 to the negative 5. Now that is not quite what we talked about in AP Chem or even in second semester organic. Let's go back now to this concept of a strong acid. When we have things like HCl or HI, these are the strong acids, and we're going to have to revisit these eventually, HBr and so on, nitric acid. Okay, these are the strong acids, and they have these crazy high Ka values. For example, with HI, the Ka value is 3.6 times 10 to the 9th, pretty high. HCl is 1 times 10 to the 6th. Okay, and we could talk about the others here, 1 times 10 to the 9 and so on. And we should talk about what that means because, again, this does relate to organic chem eventually. Okay, HCl becomes H plus and Cl minus. But we don't have an equilibrium arrow here because it happens with 100%. And so there is really no Ka value or Ka expression here, because what would you do if you had Ka expression? You would put this and then Cl minus, but you don't really have HCl here, right? There's no HCl because it's 100% gone. Okay, but that tells us something here about the Cl minus and other conjugate bases. So here's a Cl minus. I want to start drawing it like this because that's going to relate to organic chem. You have Cl minus, you have an I minus, right? And so you have that situation there. Okay. I think we can draw that, right? Okay. These are stable. In other words, as you can see from this part here, that the Cl minus is alone and it stays alone. It does not regroup with hydrogen, and so these are considered to be very stable, right? So there's a reason why that we see them alone, because they do that very well. What we're going to find in organic chemistry is that these make good leaving groups. And that has to do with what are called substitution reactions. So later on, we're going to learn about substitution reactions and how certain things leave a substrate and are replaced by others. let's now look at something else here. We should talk about the pKa value. And the way we're going to do that is remind you that pKa, when you take a p-value, right, you're taking the negative log of something. And not necessarily concentration, but in chemistry it always is. Okay, the p-value. And if we said we had a hydrogen ion concentration of something like 6.2 times 10 to the negative 4 molar, we know that that's acidic. We know that that's acidic. What we're going to do, though, is if we take the negative log of 6.2 times 10 to the negative 4, part of the reason we're taking the negative, or at least why it's useful here, is because that way we end up with a positive value for our P number. Now, because we're taking the negative log of hydrogen, we call this the pH value. So let's do that on the calculator here. 6.2, take the log. And so I didn't take the negative sign, but you can. That's 3.21. So with a pH of 3.21, and by the way, you need, because this has two significant figures, these are your two significant figures. This does not. Okay, all that does is tell me how far I am from 0, but this is actually the significance. All I'm showing you is that when you take the negative log of a value, that's called the p-value. And when you take hydrogen, that's called the pH. What is useful for organic chem is what are called the pKa values. That's how they do it. Okay? And the reason they do that is because that helps us rate whether something is a good leaving group or a bad leaving group. So with a good leaving group, we want to find something that is stable. Okay? And those things with very high pKa values, right? We're going to talk about that later. We can relate the pKa values to that leaving group, okay? But I'm going to leave it to you to determine what are good leaving groups, and certainly you'll have a table and a chart. But I think it's probably worth doing a couple here. If we talk about carbonic acid, that is H2CO3, and this one actually has two Ka values, right? Because the first dissociation is HCO3 minus, and an H plus, and then it can do it again, so HCO3 becomes the carbonate ion, and another H plus. Okay. The second Ka value is always going to be smaller than the first. But let's just say that we were given a carbonic acid Ka value of 4.3 times 10 to the negative 7. That's most likely going to be the first acid dissociation constant. And that's probably what matters in AP Chem. So what we are in organic chem. So if we want to find out the pKa value, all we do is take the negative log of the Ka value. And this is what they do in organic chem. Okay, and again, if we take 4.3 exponent 7 negative, take the log, and then the negative of that, it's 6.37. So we can talk about how that relates to leaving groups. So this is just a warm-up to the idea that pKa values are very important. Let's make sure we understand the whole concept before we make our final list. Acid-base equilibrium is important in chemistry, very important in organic chemistry. The main thing you need to know is that strong acids dissociate completely, but then weak acids dissociate partially, on the order more likely of 1%, but oftentimes you'll hear 10%. We have to actually calculate it to determine, and we don't often do it by percent, but we can. With strong acids, the anion, this conjugate base, the remainder of the acid after it breaks up, that is surrounded by water molecules in such a way that H plus and the A- do not come back together. But with the weak acid, the conjugate base still has a strong attraction for H plus, and that's why it only dissociates 1%. And we can calculate those equilibrium values. We can measure these or rate these by taking a ratio of these concentrations, which will probably be the same, and divide by the original concentration. So a common example here would be acetic acid found in vinegar. It turns out it has a Ka value of this. And that tells us that the amount of products here after dissociation is very, very small. What that tells us is that A- does not like to be alone. That's really what organic chemistry people are going to look at. So what they say is A- is not stable. These are the strong acids, some of them, they're common. And see, look how big these numbers are. What that tells us is that the anion here, the conjugate base, is very stable. And so it doesn't tend to want to go backwards. And so it can be on its own. So in organic chemistry, we will find that those are called good leaving groups. They're very stable. When you take the negative log of something, that's a math function. But in chemistry, generally, we're taking the negative log of hydrogen concentrations or hydroxide. But in this case, if you take a hydrogen concentration, it's called the pH. The first term is not significant. The numbers after the decimal are significant. We need to know organic chem pKa values because that's going to tell us about whether we can determine a reaction will take place. This is not a common weak acid situation used in organic chemistry, but this example here is to show us about what are called the pKa values and how we calculate those.